Thank you for watching my session. I'm Masahiko Sawada, working as software engineer for EDB. And in this session, I'm going to talk about breaking away from freeze and wraparound. I think this session is interesting in a sense. I mean, in this talk, what I'm going to talk about is just one program in PostgreSQL, which is a very ancient program that we've been discussing for a long time. I'm getting excited to talk about this topic now. Here is the agenda. I'm going to talk about the introduction to transaction ID, wraparound, and freezing for those who are not familiar with these topics. Then I will talk about the program statement, and I will review the actual program that exists in the transaction ID and the freezing mechanism. Then I will show you some possible solutions that we'll be discussing, along with some performance evaluation results. So let's get started. Transaction ID, XID for short, is a monotonically increasing counter maintained in the Postgres server. A transaction that modifies the database data needs to generate a new transaction ID. And by using the XID, we control the visibility of loads to other transactions. A heap tuple has two XIDs, xmin and xmax on the tuple header. Xmin is the ID of the transaction who inserted the tuple. So xmin is assigned when insert and update. And xmax is the ID of the transaction who deleted the tuple. So xmax is assigned when update or delete. And xid is actually 32-bit unsigned integer, so therefore the maximum value is approximately 4 billion. In the tuple visibility check rule, we used 2 billion xids behind the current xid as in the past, and other 2 billion xid ahead of the current transaction ID in the future. Xid is a circular, so after using up 4 billion transactions, it goes back to 3. Transaction ID 0, 1, and 2 have special meanings, so first transaction ID is 3. Since it's used for visibility checks, after wraparound the rule breaks, so that is all tuples look like being in the future and will become invisible to new transactions. To avoid it, Postgres has to do special treatment for all the transaction IDs called freezing. What we do in freezing is just to add a flag to tuple header. So once the tuple is frozen, it becomes visible regardless of tuple's actual xmin value. We have to freeze all xids at least every 2 billion transactions because, as I mentioned before, that we use the 2 billion transactions as a new one and other 2 billion transaction ID as old one. You can freeze tables manually by using vacuum command, but typically auto vacuums are responsible for the detecting all the tables, and the freezing. So you can configure it by the auto vacuum freeze max age gag parameters and so on. And for instance, auto vacuum freeze max age is 200 million by default. So it attempts to freeze xids on the table at least every 200 million transactions consumed. So you can check the age of the table by using age function. So little frozen xid is xid, which means that all xids older than little frozen xid in the table are completely frozen. So age function returns the distance between little frozen xid and the current xid. So freezing a table rejuvenates the age of the table in a sense. That is, after freezing a table, the age function will return a lower value depending on the vacuum freezing age. In a case where auto vacuum cannot keep up vacuuming and freezing, the table would be getting old and reaching to 2 billion transaction old. So Postgres has two safe triggers for this case. So for 40 million transaction before wraparound, it starts emitting warning message to the server logs. And 3 million transaction before wraparound, it stops generating new transaction ID, essentially entering the read-only mode. So I think there are two problems here related to excited wraparound and freezing. The first one is the resource consumption. In order to freeze excites, we need to read the pages of the table, possibly from the disk, and make it dirty, and then eventually write it back to the disk. Also, we need to write while code for that, and freezing is indispensable regardless how the table is used. I mean, no matter how the table is updated or not. For example, we need freezing excites even on completely static tables. So in addition to that, user can predict when it happens, but they basically cannot control when we do. So I've seen some production systems where there is a job, they have a job in order to periodically run vacuum command manually instead of relying on the auto vacuums in order to control when we freeze the table. But auto vacuum will freeze, in many cases, auto vacuum will freeze tables depending on the speed of the XID consumption. Another problem is read-only mode. So as I mentioned before, if auto vacuum cannot keep up and the transaction the age of the table becomes really, really old, the database stops to generate the new excites entering read-only mode. These are two problems that I heard from often that the user face even with the latest version of the Postgres. So before moving to the solution, let me introduce some vacuum improvements that will be done. The first one is the freeze map, which was introduced in the Postgres 9.6. So we can call it freeze map, but it's actually not a new map. Rather, we extended the visibility map by adding 1 bit per page. So from 9.6, the visibility map has 2 bits per page, all visible bits and all frozen bit. So setting all visible bit means that all tuples on the pages on a page are visible to all transactions. In other words, the page doesn't have any garbages or in-progress modification. This is used by vacuum to optimize the scanning heap and are used by the index-only scan. While all visible bits helps in the visibility check, the setting all frozen bit means that all tuples on a page are completely frozen, which is used by vacuum. And since we can know whether all tuples on the page are frozen or not by reading just 1 bit, so we no longer need to read the pages from freezing purpose. So thanks to the freeze map, we no longer need to read and dirty all frozen pages, possibly reading from the disk, which significantly reduces the amount of freezing work for static tables and mostly insight-only tables. Index cleanup option was introduced in Postgres 12, setting it to false disable index vacuuming and index cleanup during the vacuum, and reducing the total execution time much. The heap vacuum is optimized by using visibility map as I mentioned before, but index vacuum doesn't have such map, so typically it needs to read the entire index relation. So vacuum still does hot pruning, even when the index up cleanup option is disabled, but leaves the data tuples on the table referenced by the index tuple. So this option is often used in order to freeze table as quickly as possible. The failsafe mode was introduced in the latest version of PostgreSQL, so 14. If the table age is older than the age specified by vacuum fail age new gap parameter, the vacuum triggers the failsafe mode. When it's triggered, any cost-based vacuum delay will no longer be applied, and further non-essential maintenance tasks such as index vacuuming, index cleanup, and heap authentication are bypassed. The vacuum failsafe age is 1.6 million by default. In the failsafe mode, the system tries to vacuum the table as quickly as possible. It might affect the foreground transaction processing performance, but it will reduce the possibility of entering read-only mode. These improvements I explained so far help in preventing and avoiding XID-related issue from happening for sure, but I still hear that freezing is still a source of annoyance to the users and the cases where it consumes disk I/O or the system becomes read-only due to the excited upper bound. Probably this is because the fact that we need to freeze doesn't change for a long time. So we have been discussing ideas that addresses these problems further. This XID-related issue is one of the ancient problems. So there are several ideas discussed in a long-time history. Leading the older threads, what I felt was that we need to check several factors when considering the solution. The side effects and the performance are obvious and true also for other features. And in addition to that, we also need to take care of the disk compatibility. Many ideas try to address the problems by changing the page format or tuple format. For example, by adding additional information to the page or tuple. If we change the page format, we will have to support the page format upgrade, which is done by PG upgrade or possibly can be done on the fly. So among many solutions that have been proposed so far, I'd like to show 3 solutions in this session. The first solution I'd like to explain is using 64-bit transaction ID, which is the idea that I mostly often hear from Postgres users who experience the wraparound issue, like why Postgres still uses 32 transaction ID. This is a straightforward approach. By using 64-bit XID, we will relieve from the suffering by the freezing stuff. Now, actually, the transaction ID that Postgres server maintains internally is a 64-bit transaction ID called full transaction ID. So what happens in the PostgreSQL, the server, when putting the XID to the tuple header is we get lower 32-bit of full transaction ID and in order to put there. So the approach is straightforward and we no longer need freezing, but the story is not simple. So basically, we no longer need to freeze XID in terms of visibility check, but might still needed for SLR authentication, such as CLOG and sub-transactions and commit timestamp. And when it comes to tuple format, so by replacing 32 XID with a 64-bit XID, we will end up adding extra 8 bytes per tuple, which increase table size and therefore database size, and the tuple header is already large comparing to other database system. So we are concerned adding extra 8 bytes per tuple. Also, there is a disk compatibility problem. So changing the tuple header breaks this compatibility. So how we can upgrade the page header to new format and how to do in the page upgrade, and what if there is no space in pages to add extra 8 bytes. There are many problems regarding to the disk compatibility. So using a transaction 64-bit transaction ID is the simple solution, but the community seems not like it for these reasons. The first idea is to replace the 32-bit XID with 60-bit XID on the tuple. But the next solution is representing the 64-bit transaction ID per page. That is, what we do is while keep using the 32-bit transaction ID on the tuple header, we add extra 32-bit transaction ID to the page, and then representing the 64-bit transaction ID by combining two 32-bit XIDs on the page and individual header. The idea was proposed very long ago and reproposed again this year, early this year by Maxim Orlov. The patch is not committed yet and under the development. So if you're interested in this approach in the idea, please take the discussion thread by subject that add 64-bit XIDs into Postgres 15. The subject says for Postgres 15, but it's actually for PG16 or later. XID in the page header is called XID base, and it represents the upper 32 bits of the full transaction ID. The transaction ID in the tuple header are offset from uses as an offset from the XID base. So the light diagram shows the typical Hill page with after applying this idea. So each tuple has tuple header, and we don't change anything on it. Instead, we add a 16 byte space to the special area at the tail at the end of the Hill page, where we store the base XIDs. Actually, we need to store two base values for transaction ID and the multi-transaction ID. The patch supports the online page format upgrade. That is, Postgres server can run with old page format as well as a new page format. And when modifying the old format page, it tries to upgrade the page format to the new one on the fly. Specifically, by adding the 60 bytes to the page footer, page special area. If there is no space for that, it reuses the xmin field in the tuple header to store the higher 32-bit xmax. So as I explained, the transaction IDs in the tuple header are offset from the XID base. But if new XID to the page doesn't fit in the page's XID base, there are 3 steps. We first try to adjust the XID base so that all transaction ID on the page can fit in. If it's impossible, try the hot pruning and freezing the tuple. And try again. Try adjusting the XID base again. If it's also impossible, slow and error. But it happened only when transaction runs for a very long time beyond the 2 billion transactions. So yes, it still needs to freeze XID, but that would only happen when we are updating the page, in which case the page is dirty anyway, so it wouldn't cause any extra I/O, which is really good. I will measure the performance overhead. What I'm particularly concerned about was the overhead by online page upgrade. I did not look at the patch in depth. I read only README briefly, but the patch could add some codes that might sometimes be quite hard. So there are 4 targets. The head is current development branch, that is PG15, and the patch is this 64-bit transaction ID idea, and the upgrade head and upgrade patch were are the same as the patch and the head, but the cluster was initialized by PG14 and upgraded by a PG upgrade after populating the tables. And I used the PG bench, and the scale factor was 500, and database size was about 7 GB, which fits in the shared memory. And the light graph shows the result. In simple upgrade benchmark, there were differences a bit between the patch and the head, but I think that is within the error range. So I don't see noticeable performance degradation between head and patch, even in the upgrade cases. On the other hand, in upgrade cases of select-only benchmark, I can see several % degradation in the patch cases. I guess it was up to 10%, and it perhaps came from the overhead by online page upgrade parts, but I will need more investigation for that. And here is a summary for the page level 64-bit transaction idea. So adding extra 8 bytes per page seems to be acceptable by community, and vacuum no longer need to process pages for filtering purposes, but might still need for the SLR truncation. Online page format upgrade is awesome, but there seems to be some overhead. I still need to investigate for that, though. The patch is still under the development, so needs review. A variant of this page level 64-bit transaction ID is that we have 64 transaction ID in the page header as a reference point, instead of using the 32 transaction ID on the page header. That way, we don't need to compute 64 transaction ID every time when interpreting the XIDs. I just mentioned the idea to store 64-bit XID in the tuple header as a different point. The third and last idea is based on this line result. In this idea, we use PGLSN as a reference point and maintain ranges of XIDs and when each range started. PGLSN is unsigned 64-bit integer and multiply increasing counter, similar to transaction ID. And this idea is proposed back in 2013, and the POC patch was implemented by Hekidina Congress. Every pointer in the wall belongs to the exactly one range. The range can overlap. For example, looking at the bottom diagram, there are 4 ranges, and the current range is the first range. A page with a certain LSN only allowed to contain XIDs that belong to the range specified by that LSN. For example, suppose the page has LSN 600, it belongs to the third range. We can only contain XIDs between 2021 and 5002. If the current LSN is 1500, and backend is inserting the tuple and updating the page to page LSN to 1500. It has to freeze all XIDs on the tuple on the page older than 51,000 before inserting the page, in order to avoid visibility by violating visibility check rule. So I visualize this idea. LSN move from left to right. It's like a time. It's like time. Suppose there are 2 transactions running. I draw them as let arrows. Suppose the subsequent transaction started and running. What this idea does is create a range of XIDs and remember the LSN where the range started. In this example, we started the first range at LSN 100, and the range of XID is from XID 1002 to 3002. A new range is created whenever we reach the end of the current range. The lower bound of the new range is always running a transaction ID, and the upper bound of the new range is just the old upper bound plus a fixed number, 2000 transaction ID in this example. 2000 transaction ID is too small in practice, so it's just for this explanation. Likewise, a new range is created like this, and therefore there are total 3 ranges. When updating the page whose LSN belongs to the old page, it means all tuple on the page was modified long before, so we need to freeze them. And again, when updating a page, we freeze all XID on the page belonging to an old range. That way we can freeze tuples without extra ID cost. A new range is created whenever we reach the upper bound of the current range. The page that doesn't contain any dead tuple doesn't need to be dirtied for freezing ever, which is awesome. And since we don't need to add extra information to the page, so there is no page format breakage, which is also great. I reversed the patch to this XID range patch to the current head and fixed some bugs, and I've run the same benchmarks as I showed before. The right graph shows the performance result. I didn't see any noticeable overhead in both simple update and select only workloads, which look very good. But I didn't test the case where the range switching, so there might be potential overhead there. So I think I need to investigate it further. Here is summary for XID range idea. There is no page format change, and we still need to freeze XIDs, but it's done without extra IO cost. And vacuum will no longer need to process pages for freezing purposes. I think this is very clever idea, but the development seems to be stopped after 10 months discussion, so we will still need to review this idea, so there might be potential problems. And the conclusion. So we are living with the XID Wraparound program and the freezing program for decades. So freeze mob and other improvements dramatically improved the situation, but the issue still happens. So one was a promising idea, a promising approach. The page level 64-bit is under development for Postgres 16. And another promising approach is the XID ranges idea, the third one. Probably we can visit and reconsider this approach too, because the biggest advantage of that approach is we don't need to change the tuple and the page format. Apart from what I explained in this session, we will have to consider other things like serial truncation and how we allow the transaction to run longer than the 2 billion transaction and so on. We are open to new ideas, so if you have any ideas, please let us know and we can discuss on the hackers mailing list. Thank you for watching my session.